So the next
I think
talk
we
is
said-
the next talk is by Professor Hart, an assistant professor of practice with the College of Natural Sciences at the University of Texas at Austin, and a postdoctoral fellow affiliated with the Building-Wide Intelligence Project and the Learning Agents Research Group. His current research focuses on semantic mapping, autonomous human-robot interactions, and AI representations and architectures for service robots. And today, he will be speaking about signaling to peers using human-inspired communicative cues.
Should I go ahead and launch in?
Yep, whenever you're ready.
I think I need screen sharing enabled.
Let me make you a co-host really quick.
No problem at all.
Yeah, you should be able to screen share now.
Okay. All right, does everyone see my slides? Does everyone see the full screen version? I think I have the wrong screen highlighted.
We were able to see the slides.
Were you able to see?
The slides, yeah.
So, and it's taking up the whole screen, it's the full screen?
Yep.
Great. Okay, right, so thanks Pranav, nice intro. I think that my bio is a little bit updated since the stuff that I sent over. So I'm actually I am still an assistant professor of practice, and I'm at UT Austin with the computer science department. I'm also the assistant director of Texas Robotics, which is our big campus-wide research group, which encompasses all of research and education in the areas of robotics at UT Austin, crossing departments like aerospace engineering, mechanical engineering, also computer science and electrical engineering. And yeah, the title of my talk is Signaling to Peers Using Human-Inspired Communicative Cues. I probably could have tweaked that a little bit because I'm actually going to talk about a few different things today. But you know, here are the big themes that I'm going to talk about. One is what are RoboCup and RoboCup at Home? These are student competitions that researchers in my group work on that I think will be of interest to all of you. I'm going to talk to you a little bit about gaze, you know, what you're looking at, and interaction, and in particular human-robot interaction. And then I'll talk about studies leveraging these social cues. So just to kind of kick off, RoboCup is an international competition in which robots play soccer against each other. So this is probably the largest robotics outreach event in the world, at least at the university level. It's one of the largest research efforts in the world. And it really is an event that has kicked off and pushed forward a lot of interesting research in robotics. It's really helped forward the state of the art. There's this statement on the robocup.org website under the heading, The Dream. And it says, by the middle of the 21st century, a team of fully autonomous humanoid robot soccer players shall win a soccer game, complying with the official rules of FIFA against the winner of the most recent World Cup. So that is a pretty big goal. You know, that is significantly ahead of anything that we can accomplish with robots today. And yet we are able to do quite a few impressive things that have been advances that have been made through the pursuit of this goal. I'm going to show you a little bit of footage from a robot soccer match from a few years ago. This is UT Austin Villa, the UT Austin robot soccer team. They're against Bielefeld's team Be Human, LOL, right? Because they all want to be human, and they're also Bielefeld's humanoid team. This is what's called Standard Platform League. So in the Standard Platform League, the idea is that everyone's using the same robot, and the thing that's important that makes, you know, the teams distinct from one another is the software running on the robots or the machine learning algorithms running on the robots. So, you know, with that constraint in mind, this is mostly a competition of artificial intelligence. It's mostly a competition of being able to do the most with the resources that you have available on those Aldebaran Now robots. I'm just going to replay that video for you real quick though. And, you know, we'll look at a few things that kind of transpire while these robots are playing soccer. So you saw that one of our robots made a pass to another one of our robots, and then the robot kind of sees the ball. So the robots didn't make any kind of eye contact and communicate to each other, hey, I'm about to pass you the ball. They do communicate over a wireless network, but the information they can communicate is stuff like, this is where I think the ball is, this is what I think your role is in the match right now. So it's a lot coarser grained than what people communicate, and yet it's also sort of interesting in that they're talking about exact ball positions and things like that, stuff that humans can never communicate to each other. But what they're not doing, and what people do, is make eye contact. Those robots do have cameras in their heads. When it looks in a direction, that's what the robot's looking at, right? So you can kind of tell what the robots are looking at, But one of the things that the robots aren't doing is they're not looking at what each other are looking at. People do that all the time. That's going to be an important theme of this talk. So the Standard Platform League is one of a number of leagues that play robot soccer. And there's another league. I gave a talk at this group's conference this summer, also telepresent due to coronavirus. This is the Humanoid League, and here's their league photo. And what you can see is that there's actually quite a variety of robots that play soccer just in this league. There are other small robots that are kind of the same size as the Aldebaran now. There are medium and large robots. They are sized based on a number of factors, just from being sort of small, and there are sizes and weights that dictate small to large to something called teen humanoid and adult humanoid. So here is a picture from the, I think this is teen size humanoid final. You notice that there's a difference between this field and the field with the nows on it, right? So you can buy a whole bunch of Aldebaran nows and you can field a whole team of them, right? But once you get to adult-sized humanoids or teenage-sized humanoids, you're talking about systems that probably cost you about $100,000 a piece to build. There are two people on this soccer field, not because they're playing soccer, but because if the robot falls over, which happens all the time, and it hits the ground and it breaks, you're talking about a break that could cost tens of thousands of dollars to repair. These are also custom platforms. There are things that were built by the teams, not all of them. There are robots that you could buy that roughly fit the form factor. But I do think that everyone presently competing manufactures their robots in-house. The one on the left I really like because it's 3D printed. I'm a big 3D printing enthusiast. One thing it is kind of cool about that is, of course, that sections of the body in the hull, if that thing fell over and broke, they could go and they could manufacture a new part within a week very, very cheaply, right? The one on the right is, of course, manufactured using standard machining techniques. The guts of it look a lot like modern robots tend to look like on the inside. You see lots of flat planar aluminum pieces, which were manufactured on something like a CNC mill. So they built this in-house, and if they broke it, they could probably replace it. But of course, very, very different manufacturing techniques used to manufacture both of these robots. So the league that I'm actually more involved with is the Home League. And I'll tell you all about this. I'm on what's called the executive committee of the Home League and the RoboCup Federation, which means that I steer the direction of the research and the competition for a league. So one of the things that I do is I determine what do we want to be accomplishing in the next 10 years as part of the Home League? What are our research goals and our objectives? So RoboCup at Home focuses on domestic tasks in simulated living spaces. If you think about, why we might care about this, you might consider maybe you have an elderly relative, or maybe you're thinking about, hey, in 60 years, I'm going to be old myself, right? And, one thing that you probably don't want to do, if you can avoid it, is move into a nursing home. Maybe you want a robot that can help you maintain independence for longer. That's one of the reasons that we pursue domestic robots. Or maybe you just want to, not spend the weekend cleaning your home. You want to come home and everything's set and you have an amazing meal and whatever, and you watch TV or hang out with your friends or whatever it is you do in the evening. You like a robot to be doing all those tasks. So that's kind of what we focus on here. We have an arena. It's not a soccer field. It's a simulated apartment built out of this sort of, stall furniture that they use at conventions. To kind of outline what you can see in this picture, you can see that if you look straight back, there's a sort of hallway, and at the end of the hallway, there's a bedroom. There's an inflatable bed on there. And, one thing that happens at RoboCup at Home and at RoboCup in general is people work all year. They really want to win this competition. So they work day and night once they show up at RoboCup. And so people do actually sleep in the beds in the RoboCup at Home arenas because they're working really hard. They sleep on the couches in there. But, there's a bed in the bedroom. There's a desk. There's like a little spot for a computer. Area right in front of you is sort of the dining area. In this photo, the dining table has been moved out of the picture, but there is usually a dining table there. It kind of backs up to a kitchen, and then there's an actual dishwasher that the robot's supposed to load in the kitchen. There's a sink in the kitchen. There's a bunch of fruit on the table. There's a TV viewing room. There's different little entertainment nooks, entryways, and things like that in this arena. And what we're focused on is, the stuff that a robot that you might buy and put in your home would want them to do. We split this up roughly into two categories of tasks. There are the housekeeper tasks and the party host tasks. So the housekeeper tasks are all about planning and scheduling and reasoning. I know that you just heard a talk from Risto Mikkalainen. He talks about similar stuff, like the underlying planning technologies that we've used for this are as one of his core areas of research, and I assume that he talked about that in his talk. we have things in this stage, but there are other problems once you get into the robotics domain. So for instance, if you're using object recognition, you're probably using a deep learning representation. So how do you go from a deep learning representation that's saying like, this is an apple in my picture, to a planning representation that gives you the atom apple to reason about all things that you could do with an apple? So there are a bunch of interesting architectural challenges to building practical robot systems that you would actually want to put in your home. One of the themes of my research is that we really don't know what a comprehensive robot architecture would be, such that if you were a robot company and you were building an application for your robot, what would the software libraries be? We don't have the equivalents of like the windowing libraries and POSIX threads library and things like that for robots, but we're working on it. So that's one of the themes of my research. But the housekeeper task here, we have this stage 1 task, clean up, which is like all the toys are on the floor, the remote control is not near the couch, there are cups on the living room table, put everything away. General purpose service robot is kind of like, if you picture like, a Google Home device or an Amazon Echo device, and you're used to talking to this device, and the device will do something. It's usually like set a timer or turn on and off the lights. This is sort of like that, except with the robot. It's, the robot, go get me an item, go pick up a drink for me, bring something from point A to point B, set out food. So anything that the operator can say to the robot's supposed to try to do. And, this is not super science fiction. These are very, very difficult tasks to, achieve, but we do give the operators like a list of, these are the things you can ask the robot to do. You can't say, go book me airfare, because the robot is not, programmed to do that. But there's served breakfast, which, the robot does go take food out of the cabinets, put them on the table for the user. Storing groceries is a very popular one because it's sort of a speed race as to how fast the robot can put away groceries. So there's a bunch of grocery items placed on a kitchen table. The robot picks up the grocery items, and to get the maximum score, it has to put similar things together. So if there's a Coke can on the cupboard shelf, and there's like cherry pie filling, and the robot has like a Sprite can in its hand, it should put the Sprite can next to the Coke can, not next to the cherry pie filling, or it's not going to get its points. Take out the garbage is emptying all the garbage bins in the apartment and putting the garbage bags outside. And then party host tasks focus on social things. And I'm very interested in this dimension of robotics, how we make robots understand people and how we make them understandable to people. And so the party host tasks include things like carry my luggage, which starts with the person pointing to a bag and being like, carry this bag out to my car, follow me out to the car. Farewell is, helping guests to exit the party. And then just in the interest of time, I won't describe all these, but serving drinks is serving drinks at a party. Hand me that is another task that I engineered that has to do with understanding point gestures. And then restaurant is probably our most well-known task because it takes place in a real restaurant. And one of the things that makes RoboCup at home work is that teams are allowed to show up to the arena 2 days in advance of the event. They're allowed to go and build maps of the arena. They're allowed to train object recognition algorithms to recognize all the objects that the robot will interact with. They lay down landmarks, they test grasps, they test motions that the robot will make, just to make sure that everything in their demo works perfectly. But when they go to the restaurant, we hop on a bus and we drive the robot to a restaurant, and they've never seen that restaurant before. So that is a brand new thing. The robot can't possibly have a map. You have to engineer around all the unknowns that are things that we typically program into a robot. So I'm going to show you a few videos from RoboCup at home. Here's one called Take Out the Garbage. This is us doing it in our laboratory. The robot that you see in this picture is a Toyota human support robot. That is Toyota's current effort towards, actually selling a domestic robot. They've given us 2 of them that we work with at UT Austin. The robot's using a technique here called visual servoing to look for the top of the garbage can. And so it has an object recognition algorithm that recognizes the top of the garbage can. At the time that we did this, the state of the art was that you could get a bounding box telling you where the top of the garbage can was, but you notice that the robot kind of tries the wrong grip at first, right? And that's because the object recognition algorithm actually doesn't tell you the orientation of the handle, it just tells you where it is. So we programmed a special grasp that would go, okay, boom, try it like this, then try it like this. And it will always be able to grab the top of the garbage can like that. It then kind of plunges its hand down and grabs the garbage bag. You'll have to forgive the camera person here. The camera work isn't flawless. He's wandering around with one of my GoPro cameras trying to get a good shot for our demo video. And the robot's going to go over to the collection area. This is typically outside the arena, but outside the arena for us is also right next to the door that people enter in. So we programmed it to not go there in case people are coming in and out. The robot does a weird little thing with its hand, and that's because the tape might get stuck to the hand. The garbage bags are always taped to fit into those small cans. So, you know, the next event here is serving drinks. The robot will talk to the operator in this one. It might be a little hard to hear, so I'll tell you what kind of transpires. The students in this picture are two students of mine, Marika and Jason. The robot's going to go up to Marika and ask her her name, and then it's going to say, hey, do you want a drink? What do you want to drink? So the robot used to have a speaker on it that would beep when it was prompting you to talk and the speaker broke. So we just have the robot say the word beep when you're supposed to talk. So the robot's going to drive over to this like bar area, and Marika told the robot that she wants a Sprite. And so now the robot's going to go, it's going to pick up the Sprite. You know, you'll notice that it doesn't move that fast. Typically we make robots to move kind of slow, and that's actually so that the robot is always safe around people. So you could make the robot move faster, and I always advocate for making the robot move faster. But in general, it's thought that if you make the robot slow enough that the person can just, you know, unconsciously get around the robot before they get hit by the robot, that is, you know, making the robot sort of passively safe. So one thing that you'll notice here is that, you know, there is this awkward interaction, and this is something that I find very interesting. This is why I focus on human-robot interaction in my research. The robot is supposed to hand the soda to Marika, and instead of like holding out its hand and waiting for Marika to grasp the soda, it sort of goes like, please be ready to receive the soda in 3, 2, 1. And you can imagine how, you know, your friends and family might think of you if that was how you were handing objects to them, right? So, you know, we do want interaction with robots to be very natural. We want it to be more convenient than just doing tasks yourself. I'm going to go kind of fast so I don't go over time here. But here's footage from our demonstration of general purpose service robot. We've engineered a system that I'm very proud of because the robot's able to reason about hypothetical scenarios. Typically, if you have a robot and you have like a fetch task, like go grab me an apple from the kitchen, the robot has to perceive the apple so it exists in the robot's object database. In this case, what the robot does is it says, I haven't seen that apple before, but I'm going to conceptualize a hypothetical apple that might be there. I'm going to go look for it. And then, you know, I may or may not find it. Once I find it, I'll have a real apple and I'll go bring you that real apple. So, oh gosh.
You want me to bring you the food from the kitchen, is that correct? Yes. All right, I'll get on that. Which kind of fruit? One apple. Okay.
So the robot has conceptualized a hypothetical apple because it never saw the apple before. You'll see that does pass the apple in this case. We have a perception module that is pretty crafty about detecting the apple when the robot isn't explicitly looking for it, which is sort of, I don't want to call it a holy grail of robotics, but it's a very important capability in RoboCup at home type tasks. So often the way robots do this is what the robot's doing now. The robot kind of says, bring me an apple. Okay, I'm going to go start searching everywhere for that apple, right? We have a module that we now run called passive perception, where if the robot happens to pass an apple, it's going to record that position anyway, so it knows what to do. We turned that off for this demo because it's important for the hypothetical reasoning module that we showed off. So what the robot has done is it said, there's a hypothetical apple in the kitchen. It could be on the shelf. It could be on the counter. It could be on the table. It checked the shelf. It didn't find the hypothetical apple on the shelf. So it said, okay, maybe there's a hypothetical apple on the counter. It actually said, oh, there's no hypothetical apple on the counter. There's a real apple on the counter. But a real apple is even better than a hypothetical apple. I'll go get the real apple. So then it goes and brings that back to Yuchen Zhang, who's a PhD student who I work with.
Is the operator here? Yes. Hi. Please be ready to accept object 3, 2, 1.
So in the interest of time, I won't show you the next part of this video, but in that part of the video, there's no apple. The robot inspects everywhere and eventually goes back and says, you know, I looked for an apple, but I didn't find one. And it says a funny thing about like, basically the hypothesis that the apple exists turned out to be false, you know, which is clearly the sort of hypothesis testing that the planner does. So let's jump into restaurant. This is significantly sped up, but you know, one thing that's interesting about restaurant is that, you know, the robot doesn't have the opportunity to map the restaurant in advance. The people can't lay down landmarks in the restaurant for where the robot should navigate. So you use different social tricks. So one thing that we do is we look for a person who's waving to the robot. One thing that's a real problem is that when we go out in public, people want the robot to do something. So people who are not participating in the competition will wave at the robot. That's horrible, but it happens. To aid the robot in this procedure, there's a person called the bartender. In this case, I'm playing the bartender. At the start of the round, and I didn't show you this footage, the bartender waves to the robot to indicate where they are. So then the robot goes and looks for the bartender after going up to patrons. This is a student who works with me, Gilbert Martinez. He's going to place an order to the robot. He just waved to the robot and the robot came over. And he said, hey, I'd like a ginger beer. And so then the robot's going to go over and tell me that it wants a ginger beer, and I will put the ginger beer in its hand, and it will drive back to Gilbert. You know, in practice, getting these complicated robot systems to do, you know, these sort of tricky gymnastics is very, very hard. So one kind of funny thing that's going to happen right now is I'm going to pick up the ginger beer, and everyone's going to go protect the robot to make sure it doesn't drop the ginger beer, right? I mean, that robot probably costs like $150,000 to build. Funny thing happened in my lab last year. A robot dropped a full can of Coca-Cola. It burst on the robot's body. We called up Toyota. We said, hey, this is what happened. You know, we were very concerned that we would have to do some sort of expensive repair. We got permission to open up the robot because the guts are proprietary. Companies protect, you know, their intellectual property as it relates to the robot. They said, sure, open up the robot, make sure everything's okay inside. It turns out that the Coke had all pooled on a completely harmless part of the robot's body, and it was fine. We took it, we cleaned it off with some window cleaner. It was no big deal, but it could have been remarkably destructive. You see Gilbert very gingerly kind of grabbing the ginger beer and everyone clapping, because actually getting that to work in practice in a place that you weren't able to map with a robot, you know, with an item you weren't able to see in advance, that's actually really, really hard. You know, here's one of my favorite rounds. This is one that I introduced last year called Hand Me That. This is TU Eindhoven from the Netherlands showing Hand Me That. And what's going to happen is the judge, a friend of mine named Alex, is going to point to objects in the arena. The robot's going to prove that it knows what he was pointing at by touching the object. And this is a pretty complicated task. You have to interpret the point gesture, which involves using like a deep learning type representation. But then you have to be able to do some 3D reasoning, which is typically not done using deep learning. Typically what you would do is you would go into a vector representation. You would go into, in this case, I think it's the map frame that the robot's reasoning over, and then extrapolate. This is where I think the point's going. And so the robot's able to interpret these point gestures all the way across the room. It's very, very impressive. Coming back to this sort of the dream statement from the RoboCup Federation, you know, by the middle of the 21st century, yada, yada. You know, it's not the case that we don't currently play robot soccer against people. So here's a match actually from a few years ago. This is the annual Trustees versus Robots game at RoboCup. The winner of, I think it's the medium or large size RoboCup soccer league, you can see these aren't humanoids, goes and plays a game of soccer against people. And, you know, the robots are pretty good. The people are still better. That's my boss, Peter Stone. He just kicked a goal against a robot on from whatever team was playing. I have my own version of this vision statement. You know, by the middle of the 21st century, and this will probably involve understanding and projecting body language, gaze, gestures, and other human-like communicative cues. Let's look at a few of those cues that were, you know, exchanged by the people playing that game. You know, Peter pointed to Ubo and he said, the ball's going to you. And then all the players on the field watched Peter's behavior to see what he was going to do once he had the ball. There's a big visual exchange that goes on here that indicates the players are open for a pass, and then there's a pass. There are two players who go for a ball, and then one player says, you go for the ball, but he doesn't say it. He just stops running towards the ball, and the other player knows that that means that he should go and get the ball. There's a person who kind of moves out, way out, farther than he needs to indicate that he's open. And then, a player moves to take a pass, and then the pass is made and a goal scored, and at the end, the players celebrate. And actually, I think that the players celebrating is one of the important things that happens during the game, because playing sports is a social exchange. The reason that people engage in these games is in part to enjoy spending time with other people. So I'm going to look at another problem in this domain. I look at a lot of problems in depth that deal with how people communicate with each other and how we can get robots to communicate in the same way. So, in this video, we see two people trying to pass each other in the hallway, and yet they don't, right? And, just look at the title of this video, YouTube, Awkward Situations, the Hallway Dance, right? If this happened all the time, this wouldn't be an awkward situation, right? It's not awkward if every day you bump into people. If people weren't good at this, it wouldn't be awkward. It'd be like, oh, this is two people bumping into each other in the hallway. It's an awkward situation because people are good at passing each other in the hallway. But robots are not good at passing people in the hallway at all. This is actually a problem that's been really studied in depth over the course of the past 2 years. And this is what I'll call the hallway passing problem. Humans pass each other gracefully when navigating shared spaces, but robots struggle to both understand people and to make their intentions understood. And so this belongs to a class of problems called social navigation problems. So if you think of navigation problems as being the things that, like, an autonomous vehicle needs to stay in its lane and is going to navigate, from Denver to San Francisco, that's navigation, right? And there are road rules and all sorts of things. Social navigation is you're going down a hallway or through an atrium in a public space, and there are people all around, and suddenly there's no law telling you how you should behave. And so you need to interpret social cues and use social cues gracefully so that everyone understands what's going on appropriately and they're able to safely pass each other. I work on a project called the Building-Wide Intelligence Project, which is a real-world deployment of service robots. We try to have them running during all the business hours in the computer science department at UT Austin. They provide real services to people in the building, like object delivery, providing directions, giving messages. And, this gives us a lot of opportunity to watch robot navigation algorithms cause huge problems for people in the building. And before we started studying this problem, the thing that made us interested in this problem is that we had what's called the PhD student visit day. And during a visit day, students show up and they learn about the PhD program and they decide whether or not they're going to come to UT Austin for their PhD. All right, so during the visit day, we had two BWI bots running, and one went to one end of a hallway that people were kind of looking into a lab through a window, right? And then one went to the other end, and then there were people standing within 1 meter of the robot, at which point the robot stops so it doesn't bump into a person. And the robot stopped in the middle of the hallway so that people didn't know how to get around the robot to get out of that situation, right? Because the robot was very much in the way, right? The robots both eventually got out of the way. So what they did is they took the long route back to where they were going. So they went back around the other side of the hallway, bumped into each other, and then turned around again and did the same thing again, right? So, what you see here is that the clear solution is for the robot to just go to the side of the hallway and get out of the way, right? But the robot doesn't understand, the person's social intentions coming out of the box, and it doesn't know how to project its social intention coming out of the box to the people. So, I have a slide on this, and I just told you the punchline of this slide, but let's just recap it real quick. Generally, navigation works like this. Go down the middle of the hallway, and when a person comes too close, stop. Or if you're really good at it, go down the middle of the hallway and treat the person as an obstacle. And it has these problems. It's unpredictable, possibly uncomfortable for people. The robot might feel like it's coming too close or too fast to a person. The people are confused by what the robot's doing because it's not communicating what it's trying to do. The robot can block passage because it just stops in the middle of the hallway. And the robots can take longer routes than they need to in order to get their job done. So they can actually do what they're doing very slowly as a result of interactions with people. So as a first guess is how might we solve this problem? We tried putting LED turn signals on the robot. We said, people drive cars and they are used to seeing turn signals. So it's not going to be a problem. And so, you know, we built a test hallway out of cubicle furniture in an old gymnasium. So this is like a 17-meter long hallway. We have one person at one end, we have the robot in the middle, and then we have the robot use the turn signal. We just see if the robot, you know, and the person get out of each other's way. We modeled the hallway as 3 traffic lanes, like on a road. So everyone's starting in the middle of the hallway, and they have the option of going into the right lane or the left lane from their perspective. So if both people go to the right, then they'll pass each other safely, right? And then we modeled 3 distances. We have deconflict, that's when the robot's going to stop because it's too close to the person. We have de-execute, that's when the robot's going to turn. And we have de-signal, that's when the robot's going to signal its intention to turn. Now, important to note here is we made de-execute the last possible minute that the robot could turn to get out of the person's way. Because what we're trying to measure is that the person understands the robot's intention based on the turn signal, not that the person is able to get out of the robot's way if the robot's already getting out of the person's way, right? So what we want to do here is, you know, the goal is not simply to pass the person, right? The goal is to understand whether or not the person understands the turn signal, right? And of course, you know, in a real world scenario, you might not have, you know, 17 meters to make this type of decision. So actually understanding each other is important in real world scenarios. We built a pilot study with 13 participants, 9 male, 4 female. We did all the standard things that you do when you work with people. We have them sign media releases so we can use their pictures and informed consent forms. So, you know, they say that they know they're participating in a scientific study, that we're not just like, you know, sampling data without their consent. And what we measured is the number of times that the person and the robot came into conflict with each other. So that means that either the person had to walk around the robot, or clearly went the wrong way, or bumped into the robot. And what we found is that participants didn't understand the turn signal at all. Half said that they interpreted the turn signal as the direction that they should walk in, and half said that they interpreted the turn signal as indicating where the robot was about to go. But, you know, as a scientist, as someone who's studying this, what's really happening is they're answering that question at the end of the questionnaire, and they're justifying whatever they did in the study, right? They're going to say, oh, I thought that that meant where I was supposed to go, or, oh, that's, you know, indicating the direction of the robot's motion. Whatever they're doing, you know, if they successfully pass the robot, they're saying, oh, this. If they don't, oh, this, right? Most acted as though they assumed that the robot would go into the right lane. Since we're testing people's understanding of the turn signal after the pilot study, we made the robot always go to the left lane, right? We made it so the chances of the human and the robot coming into conflict, if the person doesn't understand the robot, are maximized. And that way, we can blame anything where the person and the robot pass each other successfully on understanding the signal that we're giving, right? So we have this new approach that we introduced called a passive demonstration. So the idea is to demonstrate a turn signal with no explicit training period, because we want people to understand the robot in the wild. We want people to understand it, you know, without like a tutorial, right? Like we can't go, oh, you're entering into the computer science department. Since this is your first time in the computer science department, you might see one of our robots. Let's give you a half-hour explanation as to the robots, even though you're trying to register for classes for the semester, right? Nobody would do that. We need them to understand the robots the first time. So the passive demonstration is the robot does a turn using the turn signal before it becomes important to the interaction with the person, right? That way the person's seen the turn signal and now they understand it, right? We built what's called a 2x2 study. So if you all understand, you know, your independent variables and your dependent variables are the ones that you're controlling, your dependent variables are the ones that you're measuring, right? So our independent variables are whether or not the robot does a demonstration, whether or not it shows the use of the turn signal events, and whether or not it uses a turn signal. This way we're able to measure the relative contribution of like how important is the turn signal and how important is the demonstration in our results. We did the same study again. We recruited 47 participants. They did all the same things they did before. And here are some videos from that study. So this is no demonstration and the robot's not using an LED. So the person and the robot start, you know, walking towards each other. And then they stop because they almost bump into each other. The person just walks around the robot and the robot starts moving again. So that's sort of our default condition. That's what the robots do with no additional programming. Here's the LED, but there's no demonstration. So you'll see the robot going down the hallway. You'll see it flash its LED. You'll see it, the person doesn't really seem to know what to do. Eventually, they kind of get past each other, but the robot comes all the way up to the person before the person steps over to the right. Here's a demonstration with no LED. So there's no real cue as to what the robot's intending to do aside from its motion. So it does the demonstration by moving into the right lane, then goes into the left lane, and the participant still also goes into that lane, coming into conflict with the robot. So that was no good. But here's our demonstration with the LED. We see the robot do the demonstration early, right itself into the middle lane. Now it's going to blink its LED, and clearly the person already understands that they're getting out of the robot's way in advance, right? Our results showed that this was really effective. 100% of the time with no demonstration and no LED, the robot and the person came into conflict. If I was falsifying these results, I would not say 100%, right? I'd put some fudge factor there, but 100% of the time. 90% of the time with no demonstration, but using an LED, they bumped into each other. Demonstration, no LED, and demonstration LED. The stars at the top of the chart, the 2 stars mean that this was highly statistically significant, meaning that we're able to accept this hypothesis with a great deal of confidence. If we repeated this study 100 times, we would expect it to arrive at a different result only one time. And then those error bars, or those are standard deviation bars, show the range of our expectation of the sample variance. So I'm going to ask another question, and there's only a few more slides, so I'll get through this quickly. I'm going to ask the question, what role does gaze play when people pass each other in the hallway? So gaze is what's called implicitly communicated. So you look because you want to see something, but other people can also see what you're looking at. And this is what's called joint attention, right? So if I'm walking down a hallway, I will look towards the floor roughly where I'm about to walk, so that I can see there's nothing that I'm going to trip over, or there's no hazard, the floor isn't wet, right? I'm just going to do that naturally. But everyone else will also look, just based on experience, to my eyes to see where I'm about to walk. And then they'll use that information to coordinate the behavior. And that's how people pass each other in a hallway without having any problem. Well, that makes a great story, but we still need to scientifically prove that statement, right? So what we did is we did a study where we recruited what are called confederates. So a confederate is a person who is a member of the staff of the scientific study who are going to pretend to be participants in the study. So they're going to pretend that they don't know what's going on. So what we did is we picked a very busy hallway that is used during class changes at UT Austin. We had the confederate walk and look in the same direction, which we call congruent gaze. We had them walk opposite to the way that they were looking, which is not what they would naturally do. We called that incongruent gaze, and we had a no gaze condition. And then what we did is we measured the number of times that they physically bumped into other people in the hallway. And believe it or not, our institutional review board totally allowed us to do this. We have published a study where we're measuring how many times people bump into each other in a hallway, which is one of my favorite things ever. This particular study was actually the idea of my collaborator, Ruth Mirsky. And what we found is that in the congruent gaze condition, people still bumped into each other like a quarter of the time. And that's because this is a really, really busy hallway. So, that just happened. Hundreds of people, will cross through this hallway during a class change. Incongruent, however, went up to 41%. And that was statistically significant, as is indicated by that star, meaning that if we did this study 20 times, we would only expect the opposite effect 1 in 20 times. And then no gaze, we had people look down at their cell phones, so it was clear that they weren't looking. And that only resulted in 28% conflict. And, we haven't proven this, but, one can sort of intuitively understand why this would only give a slight increase in conflict, right? Because other people are going to say, that person's a danger to themselves and others. Clearly, I'm going to give them a little bit more leeway because they're going to bump into people, right? And, here's some video of what it looks like. Here's my collaborator, Ruth. This is the congruent look, incongruent look, and then no gaze. So, the point of this is to test it on robots. So we did build this on a robot. We used the same LED turn signal as before, but we implemented a gaze algorithm on a robot head. So at the time we didn't have a robot head. We have built a robot head that we just finished this month. This robot head is called the Maki 3D printable robot head. You can actually go to, I think it's hellorobo.com. No, that was someone else, but you can go to the Maki 3D printable robot head website. download their STL files, and build it using a 3D printer, which is what we did. And then so that we could do this back then, and so that we can compare 3D printable robot heads against 3D representation, what would be called a virtual agent. We took the 3D printing files, the STL files, we built meshes out of them, we imported them into the Unity game engine, and then we rendered them like this. And using Unity, we're actually also doing tests with the robot head in virtual reality. So we're able to test this as rendered on a monitor with a 3D printed version of it and in virtual reality. However, in this case, we're only going to show on the monitor. But what we're going to do is we're going to use the robot's head to cue what lane it's about to switch in, just like a person by looking into that lane, right? So, this is what the LED cue looks like. And then here's what the gaze cue looks like. So the setup is, the same as last time with one exception. The robot's not going to signal until it's within 4 meters of the person rather than 7 meters. And the reason for that is we had an electrical problem. We had to change out the sensor, and the new sensor wasn't as accurate as the one that we were using. So we were only able to detect people from 4 meters away. We recruited 27 participants. We did an LED condition and a gaze condition. What we didn't do is none of these have that passive demonstration. And the LED condition resulted in 100% conflict, which agrees with the previous study. And the gaze condition showed a big improvement, 50% conflict. That isn't as good as the passive demonstration was, but there's no demonstration, and the robot's actually doing the signal closer to the person than they were in the previous study. So there's less time for the person to react. So, gaze wasn't perfect, but it significantly improved over the turn signal. And, this is what this looks like. We don't have the turn signals mounted on the back of the robot this time, so you can't see them like you could in the previous set of videos. But here you will see that, the robot will use its LED, and the participant will walk right up to the robot, and then eventually they kind of get out of each other's way, right? And then here we go with the gaze condition. And you can see that well in advance of getting close to the robot, the person gets out of the other lane. Now, the robot's turn is still at the same distance, so the robot doesn't start turning as soon as they see the person. And we're actually working on studies of that right now. Just to recap what we went over here, I talked about RoboCup and RoboCup at home. I talked about human-robot interaction and the validation of HRI principles using human studies. And then I introduced this hallway passing problem and discussed the role of gaze and passing each other in the hallway. So, with that, I'll open it up to questions.
Yeah, thank you. So if anyone has questions, please feel free to unmute.
Yeah, I have one question. So first of all, thank you for the great talk. And so my question is, how does this overlap with autonomous vehicles? So last session, we had a professor from CMU, Professor Maxim, and he talked about perception, localization, path planning, and actuation, and actuation for autonomous vehicles. So how does that necessarily overlap with this, if it does?
Yeah, so our starting point is actually very similar to that of autonomous vehicles, right? So both systems will use like a simultaneous localization and mapping method to determine where the robot is and where it could go. We use similar instruments. So most autonomous vehicles will use the Velodyne VLP-16 puck as its method of, perception. We also use the VLP-16 on this robot. The algorithms tend to look the same at the lowest levels. The algorithm that our robot uses to navigate hallways around UT Austin by default right now is something that is similar to what's used on an autonomous vehicle. It was developed for robots operating inside buildings, but it's similar. The algorithm that we use in this experiment is a completely custom algorithm that's designed for navigating around people. But for the most part, the algorithms that robots use to navigate around people or on highways are very, very similar. And then you kind of implement some constraints on those algorithms. So the starting points and the underlying algorithms tend to be very similar. But then in these social experiment cases, what we're doing is specializations on those algorithms. But to give you an example of other places where they overlap, we do have a robot system that we're working on right now, which does deliveries around the UT campus. It'll go to the cafeteria, pick up items, put them into the robot, and then deliver them to the person who ordered them. And one of my collaborators works very extensively on the types of SLAM algorithms and stuff that you would use on a car, but then the customization to these different environments. So there's a lot of overlap there.
Yeah, and then I just had one more question. So what are the main types of sensors that you guys use, like a camera or like a LiDAR? Or...
Well, that evolves constantly. So we have different versions of this robot. Even in the picture I showed early in the presentation, there were 3 very different versions of the robot. We're currently working on version 5 of the building-wide intelligence robot. The sensors on the version 5 will be the VLP16 puck, the Hakuyu erg, and the Microsoft Azure Connect. So the Azure Connect's a point cloud camera. It's a depth camera. So it's like a picture plus a depth. You get 2 images off of it. One's an RBGD or an RBG image, like a 4K video, and then one's a depth image, which is sort of like a picture, but every pixel is just how far away that pixel is. Then you can pop out, you can rectify that data, or you can reconstruct that data depending on what you want to do. You can get a point cloud out, and then that point cloud is sort of the 3D information. So that's probably my favorite sensor at the moment. But then the VLP16 gives you similar depth information in a 360 radius around the robot. And then the erg gives you similar information as well. The erg is what we call a 2D LiDAR, which is used usually to detect like where the walls are. And then the puck is what we call a 3D LiDAR, which is intended to give you like a big point cloud. And then the camera, you can kind of point to what you want. You can get color on top of it, much higher resolution sort of thing, in color. Yeah.
Okay, thanks.
Yeah.
Does anyone else have any questions?
Okay. If not, thank you, Professor Hart. Your talk was amazing. It was super interesting learning about robots, especially for the soccer game. That was very interesting to me.
Well, cool. Well, I had fun. I hope you all had fun. And yeah.
All right. Thank you.
Thank you. Thank you.
Thank you. Absolutely.